Hi everyone, I'm Yao Chen from Peking University. Today I will introduce our recent work, DCAPS, Dynamic Cache Allocation with Partial Sharing. It's a joint work with Michigan Technological University. In modern multi-core processor, on-chip storage resources are built in hierarchy. Each core has its own private L1 and L2 cache, while last level cache is shared by all the cores on a CPU chip. The gap between each level's access latency is very huge. A L1 access costs about 4 cycles. L2 costs 10 cycles. L3 40 cycles, and memory up to 300 cycles. The serious mismatch between high-speed CPU and large memory access delays leads to system performance degradation, which is so-called memory war. Last level cache is the last chance to avoid expensive memory access. Our goal is to increase the hit rate of last level cache through reasonable last level cache partitioning to improve system performance and fairness. Here is a classic example. A cache polluter such as streaming program runs on core 0, and a cache-sensitive workload runs on core 1. They share the last level cache freely. Though the former benefits little from large cache occupancy, it may occupy most of the cache, while the latter, which benefits a lot from more cache occupancy, cannot get enough cache resource. Under the default full share policy, workload gets cache resources based on their demand. However, a higher demand for cache doesn't always correlate with a higher performance for additional cache resources. The demand that brings no benefit actually is a kind of resource pollution. A more reasonable distribution is to control the cache polluter within a small area. That's the motivation of cache partition. Existing last level cache management involves software and hardware cache partition. A very famous software method is page carrying. It modifies the operating system to remap pages and can be applied to a real machine. Unfortunately, modern processors introduce hashing algorithm for memory address to cache set mapping. Page carrying no longer works in these systems. As for the hardware method, they are primarily evaluated in simulators. Simulation has several limitations, such as slow running speed and inaccuracy. A typical simulation-based study may only simulate several billions of instructions for workload, which is equivalent to about 1 second of execution on a real machine. We believe the complex structure and behavior of an application cannot be represented well in such a short execution time. Besides, additional hardware support makes it hard to adopt them in a real machine. However, inter-resource director technology gives us system researchers an opportunity to manage last level cache in a real machine. It can be used to monitor and allocate last level cache without additional hardware support. Cache allocation technology implements way partition with a constraint that a partition must be from consecutive ways, and a program can have its dedicated weights while sharing some weights with others. This feature allows us to complete partial sharing easily. Almost all existing studies of CAT are targeting quality of service. They provide high priority programs with enough and dedicated cache resources while leaving the low priority programs to share the rest. This simple usage of CAT does not require a fine-grained control. DCAPS aims to achieve another performance goals as well, such as minimizing misses, maximizing throughput, or ensuring fairness. In this case, complete resource isolation may damage system performance, since CAT is a coarse-grained and the number of ways is limited, so partial sharing is a good option to trade off granularity and pollution. Let's see a real system example. Two spec CPU 2006 benchmarks, SJ, ENG, and MCF are executed on two separate cores on an Intel Xeon machine, sharing a 4-way last level cache with 1 megabyte per way. We experiment with all possible CAT allocation schemes and select the best isolation scheme and the best partial overlapping scheme that maximize the total instruction per cycle, namely IPC. The left figure shows the allocation layout of the three schemes, and the right figure shows normalized IPC when compared with full sharing. It is notable that the partial overlapping scheme outperforms the other two. In some cases, the isolation scheme is the best, and in some other cases, full sharing maximizes the total IPC. Actually, complete isolation and full sharing schemes are two special cases of partial sharing, and only the fine-grained mechanism is able to scale to a large number of cores or programs. So, this is the targets of our DCAPS. We aim to implement a framework that dynamically monitors and predicts multi-programmed workloads, cache demand, and reallocate last level cache at a fine granularity given a performance target. Furthermore, the framework can scale to large core count. This is the design of our DCAPS. Firstly, we need to know when to reallocate the cache. The ideal situation is that we can detect when a program's execution phase switches, and every time it happens, we reallocate the cache. So we use a monitor to detect the change of system performance. Secondly, when it's necessary to reallocate cache, we need to profile the workload on each core to determine how many cache resources we should distribute to each core. Thirdly, based on each program's characteristics, we must find the near optimal CAT scheme. Since we allow partial sharing, namely overlapped allocation, it is prohibitive to explore the entire search space. Finding the optimal solution is an NP hard problem. So we apply the simulated annealing algorithm to find a near optimal cat scheme. In every step of simulated annealing, we use a prediction model to predict target performance metric for each potential cat scheme. And finally, we find the near optimal solution and enforce that cat scheme. As a good indicator of locality, misrate curve, namely MRC, serves as a popular tool to drive cache partitioning and memory management. It is a function that maps cache size or cache occupancy for an application to its miss rate. As the input of the MRC function can include all possible cache occupancy, MRC can thus determine the miss rate when the occupancy changes. Many methods have been proposed to construct MRC precisely and efficiently. These studies take a memory access trace as input and output its MRC when modeling a fully associative cache with the LRU replacement policy. An MRC can be obtained using online or offline access trace. Most of former researchers adopt offline because the overhead may not matter much to obtain an MRC. However, in a real system, especially in data centers, it may be impractical to profile every workload in advance. In addition, an offline MRC might be inaccurate or even useless as it is input dependent, especially when the program's phase switch is relatively frequent. So in this work, we adopt online MRC. The progress is as follows. Firstly, we collect the last level cache access trace on the fly. Especially, we need to collect the accesses to the last level cache triggered by each core. DCAPS is designed for Intel server. So we collect trace using the Intel precise event-based sampling, namely PBS. PBS has enabled tracking the linear address of sample loads and stores since the fourth generation Intel processors. You can refer to our paper for design details, and then we use resolver sampling to reduce space cost. Finally, we adopt the state-of-the-art average eviction time, namely AET model, to construct a highly accurate MRC with very low time and space overhead. If you are interested in this model, you can refer to the ATC 2006 paper. In our work, it takes us 15 seconds to construct a practical MRC during each phase, and the space overhead is less than 6 megabytes. An accurate MRC would require to track all consecutive last level cache accesses. Though we collect the last level cache access trace in real time and attempt to push the sampling frequency of PBS to 1 versus 1. However, the actual sampling frequency usually cannot reach this ideal value. In our study, we observed a rate of 1 versus 3.5 on average. That means PBS is able to catch at most 1 out of every 3.5 L2 misses. Some other factors also make our MRC inaccurate, such as cache prefetcher and the speculative execution mechanism. But one advantage of online profile is that we can record the real information with extremely low overhead to adjust our model. In this work, every time PBS buffer overflow interrupt occurs, we read the relative hardware performance counters to obtain the current last level cache occupancy, as well as the number of accesses and misses of last level cache in each core. At the time when the miss rate curve is constructed, we can also get hundreds of pairs of real last level cache miss rate and cache occupancy. We then divide the predicted MRC into several segments with these points, and then we shift these segments to make them match the corresponding real MRC. Finally, we observe a 7.5% relative error in average, which is precise enough to be used in the subsequent cache occupancy prediction. Given the MRC of a program, we can predict its miss rate as long as we know its cache occupancy. Here we design a model to predict each program's cache occupancy given any legal cache scheme. We divided the entire cache space into intervals based on all allocations starting and finishing points. Each interval is a fully overlapped sub-area of the last level cache. In this example, each workload has two intervals. One is their private cache and the other is sharing with others. The basic idea is that we calculate the cache occupancy for the program in each interval and add them up to get its total occupancy. We take the shared intervals as an example. At time 0, workload I occupies CI cache and workload J occupies CJ cache. We can get their total cache occupancy and then miss rates based on MRC. Their access per cycle during an execution phase can be measured and recorded in advance by our phase dictator. So we can predict the number of misses incurred by each program during a time slice. Cache occupancy is effectively dictated by the number of misses incurred by a program because cache lines are evicted and allocated in response to such misses. There are both positive and negative correlations between cache occupancy and the number of misses. More misses will bring a higher occupancy, while a higher occupancy leads to less misses. Assuming all Quorum programs have stable reference patterns during a phase, their misses and occupancies will remain stable after a period of time. To make it easier to understand, we assume that the replacement policy is random, so each cache line is equally likely to be evicted. We can figure out the probability that the next cache line being evicted belongs to program I, which equals to their occupancy proportion. With this probability, we can figure out their new cache occupancy after the time slice, and then we figure out cache occupancy after next time slice. Our model predicts the stable state occupancies and misses through this iterative process. During the process, during the process, we iteratively predict the miss count and then occupancy for each Quorum program. The two-program case can be extended to multi-program case easily. The random policy model works well in some cases, but fails in some others, in which there's distinct differences in program's locality, because the actual replacement policy is similar to LRU rather than random. So we take their access per cycles, namely APC, into account, and it mitigates some extreme cases. Then let's think about the parameter time slice. In theory, if we set it as 1, the iteration process will be very close to actual cache eviction process and obtain high accuracy, but a longer iteration process will bring higher time overhead. So we trade off the accuracy and overhead to assure system performance. The final time slice is 10,000 cycles. IPC is hard to estimate since many factors can influence it. Here we use a classic equation 1 for a simple approximation. IPC is a reciprocal of CPI, namely cycle per instruction. We divide the CPI into 2 parts. One is CPI of non-memory instructions, namely CPI base, and the other is CPI of memory instructions, which is evaluated as API times AMAT. The memory hierarchy we evaluate involves 3 levels of cache, a private L1 and L2 and for each core, and a shared last level cache for all cores. We apply the next classic equation to estimate memory latency of each level cache. So the formula can be expanded into equation 2. We can further divide the cycles used to access memory into cache access cycles and cache miss cycles. So the former equation equals to latency of cache access plus latency of memory access. So we finally estimate IPC with equation 4. The average accuracy for reporting IPC is 50.1%. Several metrics have been proposed to summarize the performance of a multi-program workload. Since our prediction model can predict cache occupancy, miss rate, and IPC, our algorithm applies as long as performance metric can be derived from them. In this work, we choose 5 metrics to cover different aspects of the optimization goals. And they are as follows. Average MPKI indicates the average misses per kilo instructions along the core executioning programs. Minimizing this metric means minimizing memory bandwidth contention. Throughput is defined as the sum of all program IPC. With a prediction model and the performance target prepared, we can now start our optimization process. The program is to find an optimal scheme given the performance target, since previous theoretical models cannot be applied directly. It seems NP hard problems to find an optimal partial sharing solution, so we devise a simulated annealing algorithm to search for a near optimal scheme. With performance target, MRC, and API of workloads as input, we can predict the target matrix under any potential scheme. Every prediction is one step of the whole searching process. Simulated annealing has a probability to accept a worse solution, so it makes our algorithm able to jump out of the local optimal solution. When a prediction under a potential scheme finishes, it walks to a random neighbor scheme. For instance, we choose the workload 2 as target workload and give it additional cache weight to the right. So the left figure is a flow chart of the simulated annealing algorithm. Okay, let's summarize the whole process. First, we use a scheduling controller to monitor some system performance metric to decide if we need to reallocate the last level cache. In this work, the metric is last level cache miss rate of each core. When performance degradation occurs, we consider that some programs have switched their execution phase. So we start our last level cache scheduling framework. The controller will enable the online profiles, which is used to collect online last level cache access trace and other metrics such as API, cache occupancy, APC, IPC, number of CPU cycles, and instructions. When the profile process finishes, we start searching for a near optimal cache scheme with the simulated annealing algorithm I have discussed. So when the process is over, we will enforce the eventual scheme to reallocate the last level cache. This is a diagram of, okay, sorry. This is the evaluation of our work, and thank you for listening.
What you initially said about cache coloring, that it doesn't work anymore with these hashing schemes, I think is incorrect. In fact, you get more colors thanks to hashing than less. And of course, coloring gives you better performance because you don't lose associativity. So my question is, in which way is your scheme tied to CAT, and can you use it with cache coloring just as well?
Do you mean why partial sharing with cache is better than page coloring?
I claim coloring is better, and I wonder whether you can't apply the same scheme to coloring.
Because the hashing algorithm limited the
Sorry, but that's simply not true.
The granularity of page coloring.
No, it's not. That's not true.
Oh, okay.
Good afternoon, everybody. So today I will present our work DCAT, which is a dynamic cache management method for the performance-sensitive IaaS. So this work is done by me and my colleagues, Karthik, Alex, Wes, Juan, and Yang. So today, the modern cloud, either the public or private, highly rely on the server consolidation, sharing the underlying infrastructure for multiple tenants. So the resource sharing in the IaaS allow packing more VMs, containers in a single server, so as to enable a higher utilization for the cloud providers and a lower cost to the users. However, the resource sharing also causes the performance interference among the tenants running closely. The last level cache, L3 cache, are shared by all CPU cores in the x83 platforms. So the tenants inevitably suffer from the cache flushing by the noisy neighbors running in the same socket, resulting in a very bad performance. Even worse, so the attackers can steal the information from the shared cache and compromise the cloud tenants. For example, critical CPU vulnerabilities, Meltdown and Spectre, disclosed in the last year, both utilize the shared cache. They steal some information, and they finish the first step attack because of the shared cache. So then as a result, we need smart cache partitioning. Intel introduced the cache partition techniques called CAT in the newer Xeon platform. Unfortunately, they only provide the static partitioning and doesn't support the work conserving. It means it may result in waste of the resource when some tenants are idle or not cache sensitive but still hold the cache. It also leads to the suboptimal performance when some tenants are cache sensitive but don't have enough cache assigned. So there's another challenge. Another challenge is the semantic gap between the workloads and the cache management. So as we know, the tenants running in the cloud are black boxes. We have no idea about what applications running inside. We don't know how many caches they need. So it's hard to allocate the cache for the application in advance. Sometimes even we know the application, which application is running, and we know the working set size, we still cannot allocate the right cache to the application because of the cache conflicts. Can we just assign the equal size to the application's working set? No. Let's see an example. So here, we randomly read one array and measure the average latency. So we assign a dedicated cache partition to the application whose size equal to the array size by the CAT, Intel CAT. Then we observe that the latency is still much higher than our expectation because of the cache conflict misses. That is cache line mapping conflicts. The reason behind that is that, so we store the data in the array, so it's contiguous in the virtual address. But the cache line mapping is determined by the physical address. After translating from the virtual address to the physical address, there are a lot of holes in the data. So there are still a lot of the cache conflicts. So we measure the cache conflicts when we run the example in the previous page. So we do see a lot of conflict miss, so showing here. So that means even we know the working set, we assign the equal size cache, we still suffer significant cache miss. Then we need dynamic cache allocation according to the real-time needs of the application. So this is why we propose our work, DCAT, which can enable the dynamic cache allocation to the applications according to the real-time needs. So there are two advantages. First, we provide a guaranteed performance, which is very critical to some applications which is sensitive to the tail latency. So we guarantee the minimum performance. And we also try to offer better performance. We always steal the cache from the idle application, the non-cache sensitive application, and assign them to the cache sensitive application. When the application changes over time, we claim to the baseline or readjust the cache allocation according to the needs. So provide a overall better performance. So this is one straightforward flow for our design. For each round, we first collect the baseline performance, which is the performance for the baseline cache. This baseline cache is paid or contracted with the users. So this one is guaranteed. And then to predict the cache need, we need to collect some statistics like the L1 reference, L3, and reference and the misses, IPC. So all the adjustment, the cache adjustment, is driven by the IPC, so not the cache miss. Because some application, for example, the streaming application, the recyclic memory access pattern, they have a very high cache miss, but cannot benefit from cache. So we choose the IPC to drive the cache allocation. So we still need to check the phase change, because one cache allocation is only good for one application phase, because the application will change the pattern over time. The user may run different application in the same VM, so we need to check the phase change. So here, we just use one very simple method to determine the phase by the memory access amount per instruction. And we verify that this value is only determined by the memory access pattern, not the cache size, not the working set size. So the phase change detection is an independent module in the DCAT. So any other existing word to detect the phase change can be plugged in the DCAT. Once we fix the phase, and we will change the status of the different tenant, the different VM, according to this state transition diagram. And at any time, once there's a phase change, or one cache-sensitive application's cache allocation is below the baseline, we will reclaim at once, because we guarantee the baseline performance. So for example, to explain this figure, this is an example. At the beginning, one VM is idle, or only just run some non-cache sensitive application. So obviously, it's a donor. It doesn't need a lot of cache. At T1, this guy starts running some application. So first reclaim to the baseline. At this time, we still don't know if the application needs additional cache. So we try to add just one additional cache way and check the IPC again. We see the IPC improvement. So we keep assigning additional cache way until IPC stops increasing. Where is the preferred status for this guy? So at this moment, the cache miss and the cache conflict are negligible. So it will keep this status until the application ends. So it becomes the donor again. So we implemented our prototype in the Intel Xeon platform. The DCAT run as a daemon in the host OS. It relies on some, we also utilize some existing the library from the Intel, the CAT and the CMT, but we did extend the CMT, some interface a little bit, for example, for the monitor, because we need some additional metric, like the L1 reference. So we can easily get this information from the MSR register. This is the test bed for our evaluation. We run both the micro benchmark and some application level benchmark. For the micro benchmark, we use MLR and I'm load to internal benchmark. The MLR just randomly read the data to the array, and the MLOAD, we read the array sequentially. Then we calculate the average latency. So the first, we just run one single instance of MLR. We track the allocation status, progress, and the normalized IPC. So we can see this figure, the line trend, it's very close to our expectation in the design. It means the cache allocation matches our expectation. So we measure the latency. So compared with just assigning the equal size the working set by the static partition, we can increase the average latency significantly. So next, we run the MLOAD, but a larger working set, 60 megabytes. So it's larger than the cache capacity in the Xeon. So it means this one is a streaming workload. It has a lot of cache miss, but cannot benefit from cache. It's a recyclic access pattern. So after several rounds, we assign additional cache to this guy, but didn't see any improvement of the IPC. It's a streaming and it's a donor. We can collect the cache and assign to others if possible. So next, we run them together simultaneously. So we can see, both the MLR and MLOAD, their cache allocation are independent. So finally, after several rounds, MLOAD becomes the donor, and the MLR gets a preferred status. So here we can see the MLR's latency is increased, but without hurting the M load. No interference, and we offered better performance for the cache-sensitive applications. Next is some real application evaluation. Here, we run 5 VMs, with, each with a 4 cache array in a single socket. We run our benchmark in 1 VM and run 2 different noise neighbors. The first noise neighbor is M load with 60 megabytes. It just flush the data, flush the cache. So the look busy is a synthetic CPU burner. It just burns some CPU cycles, but doesn't flush the cache. So it's a CPU-intensive application. We run 2 M load and 2 look busy as a noise neighbor in the socket. First is a CPU 2006. We observe both the DCAT and the static partition can improve the performance compared with the shared cache because they both protect the victim from the cache flushing. Well, the DCAT can get better performance. So by average, the DCAT can achieve about 25% over the shared cache and 16% over the static partition, the CAT. We also run some, for example, the in-memory DB, the Redis, object relationship DB, the PostgreSQL, and the Elasticsearch. All of them are memory-intensive applications. With DCAT, we can improve the performance in terms of higher throughput, lower latency, or lower tail latency. So in this area, there are a lot of existing work. Most of them, for example, the CQoS, Ubiq, utility-based, and Advantage, they rely on they need additional knob to the hardware. So they just verify their ideas by some simulations. Well, our work, the DCAT, we don't need any additional knob, just running in the real system. So the page coloring can also provide some kind of the partition, but the overhead of the readjustment, repartition for page coloring is extremely high. So it's a orthogonal to our work. They can run together, just like that question. But once the phase change, we readjust the partition, the overhead for page coloring is very high. So it never entered to the real system, so didn't enter to the kernel. Heracles is a work from the Google. So it's a dedicated method for the Google data center. It divides Google's application into 2 groups. One is a low priority, another group is a high priority. So it means it only supports 2 tenants. It's not a real multi-tenant. And it assumes it already knows which application is running because it's an internal method. The Google knows which application is running inside. So there are a lot of other performance isolation in the I/O because I/O is also a shared resource in the cloud, but they don't focus on the cache. Finally, let's conclude. So since the L3 cache and the shared L3 cache and the static partition will hurt the cache utilization and result in the suboptimal performance, so we propose our dynamic cache allocation method called DCAT. We provide 2 advantages. One is a guaranteed performance, the baseline performance, and we offered better performance for the cache-sensitive applications by readjust the cache dynamically. So based on our existing the results, the evaluation, we can see up to 25% over the shared cache. For some real applications, we can also see significant improvement over the shared cache and the static partition. Thanks for your attention. Any questions?
Hi, sir.
Hi.
Thank you for your talk. So I would like to know if you know the paper which is called VCAT.
VCAT?
Yes.
Okay.
Published
I think
last
it's
year.
2017 for the RTS.
I don't understand what.
So you mean I remember it's a VCAT published last year,
Yes.
and
They
for
do
the
exactly the same work.
yeah similar. So I remember, if my memory is correct, because when the paper is released, so I already submit the paper. That one is published in some real system area in
Exactly.
the RTOS or REOS.
Yeah.
So they just use CAT to dynamically adjust the cache for some the embedded system, which is need a real-time scheduling, but not guarantee any performance or improve the overall utilization. No, it's a stock no.
Okay.
Thank you. If you go back to your slide where you've got the bar graph,
Which bar graph?
the one where you're testing against the real applications with your noisy neighbours. So,
Which one?
so that one, yeah.
Yeah, okay.
So do you have on here, do you include in any of this how much slowdown that you're incurring for your noisy neighbour? Because you're saying about how you've got a 60 megabyte amount that you're looping over, but modern Intel processors will notice that you're no longer getting use out of the cache and will change the eviction strategy to account for this. So the speed up you're getting here may well be just that you're taking performance away from your stress application. So I was wondering if you'd measured at all how much your stress applications slowed down when you removed the cache from them.
You mean if I observe any slowdown when I run the evaluation?
If you observed any slowdown in your stress applications, because you're taking cache away from the stress applications, and modern Intel processors adjust their eviction strategy to allow for applications that exceed the cache size.
Okay, for this example, there's only one benchmark running in the system. All others are the noise neighbors. I still cache from them.
But you're probably slowing, you're almost certainly slowing your noisy neighbors down by doing this. I was wondering how much
so noise neighbors are here. So why I call it noise neighbors, also we first here it's a IO application, non-cache sensitive or streaming. So they cannot benefit from cache. So, or else I will not collect data from them because we guarantee the baseline performance. If one application is also a sensitive application to the cache, so we will guarantee the baseline. So yes, you're right. So sometimes if everybody are sensitive to the cache, we don't have enough capacity to assign more cache. Everybody just maintain the baseline. No improvement, but no hurt.
I think we should probably have a chat offline about the other strategies that Intel processors now do to avoid the problems that you're describing, because it's not as simple as you're making out. But thank you.
Thank you. Yeah, we can talk more. And I didn't show more details in the talk because of the limited time. Please find more details in the paper. And feel free to ask for a demo if you are interested in. So, yeah, thank you.
Christopher Stewart, Ohio State. I just wanted to maybe follow up on that, and I wanted to know if you have begun to consider linking to application level metrics with this baseline approach that you're applying, because when you have multiple workloads that are hosted that both need the cache, it seems like your baseline approach is going to overshoot, and your scaling out approach, your approach to detect the preferred cache size is going to overshoot. And it seems like you would want something that is really fine-grained once you have multiple applications running that are competing and both depend on the cache.
Thanks for your suggestion. Yes, so far we just use a very simple metric, IPC, because this is one straightforward metric we can collect outside, because in the public it's a black box. We cannot know which application is running. It's a little bit hard to know from the application level. So it's a good method. And another one is that if we run multiple applications in the same VM, so some are cache sensitive, some are not. So if the mix is still the cache sensitive, because overall, from the view of the outside, this guy suffered the cache miss. And if I assign the additional cache weight, the overall IPC will increase. So it means the non-cache sensitive application in this box, no hurt, but the sensitive guys can benefit.
Hello everyone, my name is Jie Zhang from Yangsan University. Today I will talk about our work, which is a new accelerator design. Firstly, please allow me to use a single slide to summarize this presentation. In traditional heterogeneous system, to transfer data from SSD to the accelerator, the data need to go through a long data path from the SSD to the DRAM to the CPU and finally arrive in the accelerator. During this procedure, it will cost a lot of power consumptions. We propose to use a flash backbone instead of the SSD, and we propose to use the multi-core low-power DSP platform upQs instead of Xeon Phi. By integrating the flash and upQs as a flash upQs, our new platform can reduce the power consumption as well as eliminate the data movement overhead. So our flash upQs can improve the performance by 127% compared to the traditional heterogeneous system. It also can reduce the energy by 78%. Heterogeneous system, including the CPU and accelerator, is popular in the system design. For example, there was a large portion of the world's top 500 high-performance CPU has employed accelerator nodes. So accelerator is promising, but it still faces several challenges. One of the concerns is the power consumption. For example, the power consumption, the TDP of Intel Xeon Phi is around 300 watts, and that of GPU is around 180 watts. However, the embedded systems such as automobiles constrain the power to 20 watts. The power consumption of the accelerator has rendered it difficult from being accepted in low-power system. Another challenge is data movements. We analyze the impacts of data movements by breaking down the execution time. If you look at the figure, the storage access and the data movements accounts for 55% of the total execution time. Even though there are some workloads which mainly spend time for the computation, we observe that the data movements accounts for more than 60% of the total energy consumptions. Such overhead comes from the discrete hardware of accelerator and the storage medium. You can see a typical computer system in the slides. If the accelerator wants to access the data from the storage medium, the data need to firstly copy from the NAND flash to the device memory and go through the I/O controller, NOS bridge, and finally arrive in the host side DRAM. The host CPU need to access data from the host side DRAM and copy the data to the accelerator side memory. Another overhead of data movements comes from the complicated software stack. The data need to go through the SSD firmware, HBA driver, file system, I/O runtime library, user application, and accelerator runtime library, accelerator driver, and finally it can reach the accelerator. During this procedure, CPU is involved in almost every software layer, which will cost a lot of CPU cycle for data movements. The next challenges is low core utilizations. As we use the low power DSP cores, it has relatively low computation capability, so its performance is easily impacted by the serial programming codes. To figure out the impacts of serial codes, we generate multiple executables which contains different ratio of serial codes. If you look at the left figure, it shows up the performance trend of executing different executables. If we increase the serial code ratio to 50%, then the performance will degrade by 6%. The right figure shows the corresponding core utilizations. If you look at the figure, if we increase the serious core ratio to 50%, the performance, the core utilization will decrease by 76%. So we propose flash up queues. It can reduce the power consumption, eliminate the data movements overheads, and also improve the core utilizations. So let's firstly take a glance of our hardware design. In traditional heterogeneous system, the accelerator and the storage are discrete devices which connected to the host through different data bus. Our new platform integrates the accelerator, NAND flash, and SSD controller into the same box and connected to the host through the PCIe. Within our new platform, the accelerator can directly communicate with the NAND flash without going through any system bus. Inside the accelerator, it contains 4 main components. The flash-based storage consists of a flash backbone, which is connected to the TI multicore DSP platform through the FMC. Within the flash backbone, we develop multiple FPGA-based flash controller. Each controller maintains the I/O transaction of multiple flash packages. The cluster of DSP cores consists of 8 low-power cores. We call it LWP. 1 core is allocated for the address translation and also for the kernel scheduling. We call it flash writer. Another core is used for the SSD background task. We call it a store engine, and the remaining cores are used for the kernel execution. The peripheral components consist of PCIe controller, power sleeve control register, scratch pad, and internal DRAM. In our new platform, we also use a terabit crossbar network to reduce the message transfer latency as much as we can. In addition to the hardware modification, we also provide the software. We also revise the program model. As you can see from the slides, in the traditional program model, the accelerator usually contains very limited memory space, so the host needs to split the user application into multiple pieces and invoke a loop which will iteratively copy the kernel and the data to the accelerator. In our flash up queues program model, as data already received in the accelerator, so the host only needs to generate the kernel and offload the kernel to the accelerator. Next, I will talk more about how to fuse the flash into the multi-core system. In the accelerator, the kernel needs to access data from L1, L2 cache or the DRAM. As accelerator has very limited memory space, so kernel also needs to access data from the storage. However, as I mentioned before, to access storage, it requires OS and the file system support, but the OS and the file system usually require extra CPU cycles, which is not desired in the low-power systems. In addition, if we want to access the data from the flash backbone, it also requires the support of flash firmware. In our work, we allocate flash writer to handle all the stuffs. As our platform do not build on the OS and the file system, so we directly expose the flash address space to the LWP, as the LWP cannot directly access the NAND flash through the normal load store instruction, so it also needs to access the, our solution is to map the flash address space to the memory so the LWP can directly access the data from the memory. For the storage access management, what we did is we maintain a simplified page mapping table which can be fed into the scratch pad. And also for every incoming request, the flash writer will do the translation from the logical address to the physical address. As multiple LWP can access the storage independently, another important role for the flash writer is to do the protection and access control. We maintain a range lock to keep the records of protection information. In addition, we allocate another core which is store engine to do the SSD background tasks such as garbage collection and log dumping. Here I provide an example of mapping flash space to the memory for the reads. As data initially received in the flash backbone, so the kernel needs to declare a flash map space by sending a message to the flash writer. This message includes a pointer to the data section, request type, and also flash address. Flash writer needs to inquire the range lock to figure out if the data has been protected for other kernels. If the data is allowed to access, then it will inquire the page table to figure out the actual physical page number. Then the flash provider will send the I/O request to the FPGA-based flash controller, and the flash controller can do the I/O transaction and copy the data to the internal DRAM. Lastly, internal DRAM will serve the load store instruction from the kernel. For the address translation, we use a simplified page mapping table. To reduce the page mapping table size, we group pages from across different channels as page group. So the logical address of the incoming request can be split into the channel index and the page group number. Then the flash provider refers to the page table with the page group number to find out the actual physical page group number, and then the physical page group number can be split into the package index and the physical page within the package. For the range lock, we organize it as like a red-black tree. Each node of red-black tree contains the address range, which is declared by each LWP. So incoming requests need to figure out if its address range has overlapped with the nodes in the range lock. Similarly, for the writes, the kernel needs to send the write message to the flash provider, and the flash provider needs to get the permission from the range lock. Then it can allocate new physical page group for the writes, but if the number of new physical page group is limited, so it will invoke store engine for the garbage collection. Next, you will send the I/O request to the flash controller, and the flash controller will do the I/O transaction and copy the data and do the DMA. At the last step, the flash provider will update the page table. Next, I will talk about more details of the parallel kernel execution of flash up queues. Conventional parallel kernel execution models such as OpenMP or message passing interface, they can do the final granular control of the task scheduling, but they also face some problems, like they require the support of OS thread management, and also it will increase the communication between the host and the accelerator. To improve the throughput of LWPs, flash up queues allow the kernels to offload multiple kernels from different applications to the accelerators. It allowed the accelerator to self-govern the kernel so that there's no requirements from the CPU interventions. Next, I will provide 3 different kernel scheduling schemes. Well, one of the most simple scheduler schemes is to allow the host CPU to bind in the user application to a specific LWP. For example, the CPU binding the application 0 to the LWP 0 and the application 2 to the LWP 2. So the kernel 0 and the kernel 1 are scheduled to the LWP 0, and the kernel 2 and kernel 3 are scheduled to the LWP 2. This is quite simple, but it also results in very poor core utilizations. We propose a dynamic kernel scheduling by leveraging the flash provider. So the flash provider can monitor the status of each LWP and assign the kernel to the LWP which is in idle. So let's use the same examples. As the LWP 0 to the LWP 3 are all in idle, so we can schedule the kernel 0 to the kernel 3 to all the LWPs. It can reduce the latencies, but it cannot maximize the core utilizations. So next, I will provide more finer granular scheduling with microblocks. The kernel can be split into the multiple microblocks, and each microblock can contain a couple of code segments, different from the kernels which can be executed in parallel. Different microblocks has data dependencies. Our flash provider maintains a new data structure which can record the data dependency between different channels, between different microblocks. So our optimized solution with the microblock scheduling is to schedule multiple microblocks across multiple kernels to the different LWPs. Our goal is to make the LWP busy. For example, the microblocks from the kernel 0, kernel 1, and the kernel 2 will be scheduled to the different LWP to make it busy. And once there's a LWP in idle, then we can start to schedule the kernel 3. But the problem of this scheduling is we need to make sure all the running microblocks has no data dependencies. It will increase the complexity of the scheduling. Next, I will talk about our evaluation. We set up our experiments with the real device. For the evaluation, we we generate a heterogeneous computer system with a discrete storage and accelerator. We also evaluate our flash up queues with the 3 scheduling schemes I mentioned before. Firstly, let's look at the time series analysis of executing one kernel in SIMD and the intra-kernel out-of-order. As you can see from the figure, this intra-kernel out-of-order can have a shorter storage access time compared to the SIMD because it can eliminate the data movement overheads. And if you look at the computation time, the intra-order out-of-order can shorten the computation time because it can better leverage the dynamic kernel scheduling. Next, let's look at the total energy consumptions. If you look at the figure, the most important thing I want to mention is the flash up queues can drastically reduce the energy consumption of data movements. Thank you for your attention.
So if I understood correctly, you're able to do these computations within a power budget, a hardware-powered budget that's sort of an order of magnitude smaller than, say, a Xeon Phi or a GPU.
Yeah.
How do you compare in terms of normalized performance per watt? So for example, if I used 10 or 15 flash abacuses to get me back to the power budget of a GPU, would I have better performance, worse performance?
Unfortunately, in our current test, we didn't have these kind of things, but I think this suggestion is quite good. Maybe in the future work, we can do these things as well to figure out how it works and how it looks like. Yes, thank you very much.
Yes.
So very interesting stuff. I have a question related to the applications that you enable with this architecture. So of course, there's been a lot of work going back on smart SSDs and then smart flash. Your architecture seems to be a little bit different. Can you give some insight on which types of applications do you, let's say there's a benefit if you use your solution instead of the kind of state-of-the-art that's already out there?
Actually, if you look at our evaluation, you can figure out like for the most data-intensive workloads. For example, as we tested is we selected workloads like Rudinia. We use like a BFS graph applications. We can figure out there's a huge benefits. And I think the reason because it can reduce the data movements overheads if the application requires to access a large amount of data. So in this application, we can have a lot of benefits. But if the data just do the computation intensive things, then I think the benefits we can provide is limited.
So hi, I'm Vlad, and today I will present to you our paper, which is called Welcome to Zombieland, Practical and Energy Efficient Memory Disaggregation in a Data Center. This is a joint work with my colleagues Boris Teabe, Alan Chana, and Daniela Gimon from Toulouse University, and Kanturk Isci from IBM Research. As most of you probably already know, in last decade we saw a shift in the computing landscape. Computers from your homes and from your university are moved to specialized data centers, and the concept around this is called cloud computing. So in reality, we see a cloud computer. Cloud computing as a giant computer, but in reality, it is a set of underutilized servers. So in the last decade, virtualization came to improve this historically low CPU utilization. But even in these cases, we can barely see CPU utilization higher than 50%. So why this 50% utilization, why this low CPU utilization is a problem? So as you can see on this curve, we have represented the ideal model, which is the proportional model, which says that the power consumption of a server should be proportional to its CPU utilization. And with the red curve, we represented the real power consumed by a server, which is the measured power. And as you can see, the real model intersects the ideal model in 2 points, which at 0% where the server is completely off, and at 100% where the server is fully used. In the intermediate states, we can see that there is a fairly large distance between the ideal model and the reality, which means that a server wastes memory. So why we cannot increase this low CPU utilization? One answer is because of the memory and because of the fact that it hinders the VM consolidation. On the left side picture, you can see the memory per CPU ratio of the Amazon VMs in the last decades. Why we choose Amazon VMs? Because we think that they represent the software demands in resources. And what we can notice is that nowadays the memory demand is 2 times higher than it was like 10 years ago. Conversely, on the server side, on the physical server side, you can notice an inverse trend, which means that nowadays the physical servers provide more and more CPU. So in conclusion, we have applications which demand more and more memory, but we have servers which provide more and more CPU. So this is one reason of a poor VM consolidation in the nowadays cloud. Recall that the energy domain in the nowadays data center is 1 server, which means that if we need more memory, we have to turn on a server, even if its CPU is not used. So one trend which comes as a solution to this problem is disaggregated computing. In disaggregated computing, we change the server-centric view of a data center to a resource-centric view. We can see a disaggregated computer as a huge computer whose resources can evolve independently. So if you need more memory in a disaggregated computer, you can just add more memory to the computer instead of turning on another server. Several projects invest in this trend, and between them we can mention The Machine from HPE or Intel Rackscale from Intel, but none of them are mainstream yet. So in this work we propose a short-term solution which can have the benefits of memory disaggregation and can be introduced with small changes to the hardware and the system software. So in conclusion, in this paper we have 3 contributions. We introduce a new ACPI state called Zombie. We present a practical rack-level memory disaggregation based on Zombie servers, and we developed Zombie Stack, which is a cloud operating system based on OpenStack and the modified KVM hypervisor. So we propose a data center where active servers use remote memory provided by Zombie servers, and the Zombie server is nothing more than an active server turned to a low power state. So before entering into the details, I will do a short background. ACPI, which means Advanced Configuration and Power Interface, is a standard that allows operating system to perform power management on individual components. It specifies 6 states for the system level, from S0 to S5, S0 being the most active one and S5 being the least active one. So in this image you can see the architecture of a modern Intel processor. We have what they call the core part, which includes the CPU core, the ring interconnect, the last level cache, and the Gen 9 GPU, and the uncore, which includes the historically NOR bridge and some other modules which are not related to data processing. Between them we can mention the memory controller, the PCI Express controller, the power control unit, and so on. So our first contribution is a new SCPI state called Zombie. It is very similar to S3, which is called Suspend to RAM, and which is represented on the left side image. So in S3, most of the system components are turned off, except the memory, which is in self-refresh mode. In the case where the user wants to wake up the server over the network, we can also keep on some other components, like the NIC, the card, the network card, the PCI Express controller, and the power control unit, which is the one which fires the turn on of the server. In the right side part, you can see represented the state of a zombie server. In addition to S3, we also keep on the memory controller. The memory is in active idle, not in self-refresh state, and the network card is completely on. The PCI Express circuitry also is completely on. So as you may notice, the zombie name is very representative. A server in a zombie state is brain dead, which means that its CPU is off and memory alive. Its memory is alive. This is another important thing, is that the RDMA cards are able to perform memory translation, which means that we can keep the CPU off. And this is very important, since it is our way to decouple CPU from memory. So this is the next generation cloud in our vision. Okay, our second contribution is a practical way to disaggregate memory using a zombie state. So in our rack, a server can play one of the four roles. It can either be a global memory controller, which manages the global memory, which manages the zombie memory. It can be the secondary memory controller, which assures transparent high availability to the global memory controller. It can be an active server, which uses memory exposed by a zombie server. All active servers in our system execute a remote memory manager, which pre-allocates memory, which means that we decentralize the fast path of memory allocation. So the zombie memory could be exposed in two ways, could be used in two ways, either as a RAM extension, which is the extension of the virtual address space of the virtual machine, or as a fast swap device. Our third contribution is a cloud operating system based on OpenStack and modified KVM hypervisor. So in our system called Zombie Stack, the Nova module, which is the module that handles VM placement, and NEAT, which is the module that handles VM consolidation, are more flexible, since in our solution, the memory of the virtual machine could be spread over multiple physical servers. Another advantage of our system is that we are able to perform faster VM migration, since we migrate only the local memory. The remote memory could be accessed from the destination of the virtual machine. So concerning the evaluation, we try to answer to two questions. First is how much memory could be tolerated by an application without a huge performance impact. And second, how much energy is saved by a data center using our zombie technology. So our testbed is composed of 4 HP machines interconnected in an InfiniBand network. And for the energy consumption experiments, we also have a Dell machine. We also use a Dell machine and a device called PowerSpy2 to measure the energy consumption. Since we don't have the physical server that implements our zombie state, we modeled its energy consumption. And for the other experiments, we replace a zombie server with a server in the S0 state. In short, a zombie server consumes around 12% of the maximum energy consumption of a server. knowing that a server in S3 consumes around 9%. But for more details about our model, I invite you to check the paper. So in the first set of evaluations, we try to answer the question of how much remote memory can be tolerated by application without huge performance impact. And for that, we performed experiments with an Elasticsearch benchmark, with a data caching benchmark from Cloud Suite, and with Spark SQL. And what we found is that a memory up to around 60% can be tolerated without a huge performance impact. In our second set of experiments, we tried to see how much energy can be saved by a data center using our Zombie technology. And for that, we performed simulations on traces from a Google data center having around 12,000 servers. And we compared against NEAT, which is the consolidation module of OpenStack, and against Oasis, which is a solution proposed by IBM. And you can find out that our solution is about 2 times more efficient than the state-of-the-art, and it can improve the energy consumption in a data center by up to 67%. So in conclusion, in this paper, we introduce a new CPI state called Zombie. We propose a practical approach to disaggregate the CPU memory tuple. And we developed Zombie Stack, which is a cloud manager based on OpenStack and the modified KVM hypervisor. Thank you for your attention. And one more thing, as the chair said, I'm looking for a postdoc, so if you need a mouse in your university, I'm free.
You mentioned that you have done some studies of how much power you actually save, but can you at least tell us here how much power does one of these fancy Ethernet cards that has all these features, the RDMA and that sort of stuff, how much power does that consume compared to a CPU? Because obviously the card still has to be active.
I don't have the table in the presentation, but if you check the paper, we have a table where in our model, we take step by step to compute the power consumption. So we also have the consumption of the card. I don't have the figures in my head, but I see the table, but I don't see the figures.
Hi, Mark Silverstone, Technion. Great talk and very interesting work. I'm wondering, I have kind of 2 questions. One is the question of the motivation. So the dynamic power consumption in data centers, to what extent is it really a big deal? Because from what, like in architecture community, people are talking about the maximum, provision power consumption of the whole data center. So the dynamic power consumption is not as big of an issue, or like what's your take on that one? And another question is more technical. Did you evaluate the possibility of moving or accessing cache lines, or like the granularity of access? How would that fare in terms of like remote accessing your memory?
Okay, so
thanks.
For your first question, I'm not sure, because I'm not in industry, I'm not sure how the energy consumption is important, but I don't think it's a problem if you can spend some energy with a data center. So your point was that you generally look on the power consumption on a long term?
I intended that the power consumption of the maximum power consumption is more important than the dynamic savings.
Okay, so the maximum in a 1 month interval, or?
No, the maximum means that if you have the worst case power consumption, that would actually matter more than the dynamic savings that it
The worst case, so the worst case during the execution the lifetime of a data center.
When I have a data center and at some point I have a peak load and I run out of power, then it's bad, right? Because I have to shut down some of my computers. So the question is, and basically the dynamic power is for free, and what really costs is this maximum allocation. So that's my question.
Okay.
Like, I'm sorry,
I mean,
we can take it offline.
So our work is not for that context. But as I said, like, I don't think it's a problem if you can spend some memory. I'm not aware about this stuff. And your second question was if I evaluated the accessing of a cache line, of the cache lines.
The granularity of memory access, was it just pages, just swapping between them?
It's kind of more than a page. Generally the size of a super page.
And if I can ask one question, Fabio Pianese, Bell Labs. Can the zombies be unzombified and come back to life if you need more CPUs? And did you examine the impact of dezombification?
Dezombification, nice term. Yeah, so kind of the details of our system. We also write all the information on the local disk. So in the case where the zombie needs to wake up, the information can be taken from the local disk of the computer. So in the worst case, you can just wake up the server and lose everything because you can take it from the local disk as a backup copy. You're welcome.